Okay, hello everyone. Today we have another ITMP research seminar, and today's speaker is Sabir Ramazanov from Prague, and he's going to talk about phase transitions in the dark universe. So please, you are good to start.
So thank you very much for inviting me. It's an honor. So I would like to start with sad news. So today, Valery Anatolievich has passed away. This, really sad news. He's one of the prominent forces in the Russian and in general in theoretical physicists, and not only a scientist but also a great teacher, and who contributed to physics also through through great textbooks, through developing of school. Some of us have been previous PhD students, graduated with Valery Rubakov. And also I want to say that while being decoupled from the Institute for Nuclear Research for a long time, in this talk, actually, most of the topics which I will cover have been, I have learned them through Rubakov's, through Valery Anatolievich's lectures, and through reading of his books, and he contributed to many of the topics through his profound articles. So I will talk about my research during the past 1 or 2 years. I will cover my research results during the last couple of years, made in collaboration with people. Some of them you may know, like Evgeny Babichev, Dmitry Gorbunov, Alex Wickman, and Rome Samantha is the postdoc, also in Prague. So Dmitry asked me, actually, Dmitry Ponovaryov asked me to make a 20-minute introduction. I'm not sure if I will be so long in terms of an official introduction, but during my talk, I will make some intermediate introductions whenever I will encounter some new object with which you may be not very well familiar. And so forgive me this slightly non-linear structure of my talk, which will consist of 3 topics: dark matter, wire-induced phase transition, domain walls, and axions in the end of my talk, which all these topics are deeply connected between each other, but at the same time, they can be understood separately. So, and this will also allow me to cut some part of my talk if we will completely run out of time. I hope it will not happen. Let me start with something very well familiar, the pot with boiling water. So the disappointing thing is that, so are there at all phase transitions in cosmology? The answer is actually that we don't know. In particular, there is no electroweak phase transition, but rather in the crossover predicted by the standard model of particles. I'm less sure about the possibility of quantum chromodynamics phase transition. However, recent lattice simulations show that it's also rather a crossover than a phase transition. So this is despite the fact that the temperatures in the early universe can reach huge values, much larger than the temperature of 100 Celsius for sure. So,
but is it still an open question? There could be some phase transitions. It's just
yeah. So I don't know, but definitely it's not a first order phase transition. Okay, definitely it's. And it can be, I think, either second order phase transition or crossover. But I read just recently that the results are showing rather crossover. But even if there is a second order phase transition, then it's a very weak phase transition, which doesn't leave much traces in the early universe.
Okay.
So, so why, if there are, so why do we care about, why do we bother about cosmological phase transitions? So there are multiple reasons. One of the first reasons, one reason is that standard model appears to be incomplete. In particular, we have problems with baryon asymmetry. We should explain neutrino oscillations and dark matter. In principle, phase transition can be possible in the extended picture. The second reason is that cosmological phase transitions, if they existed, they can bring a very interesting phenomenology in terms of, for example, domain walls, cosmic strings, and magnetic monopoles. And studying these objects, one can make conclusions about high energy scales, much larger than electroweak scales because domain walls or cosmic strings or magnetic monopoles can affect large scale structure, they can affect cosmological evolution, etc. And in this regard, magnetic monopoles have been particularly interesting and played a profound role in cosmology. In particular, if phase transitions in ground unified theory, which typically should occur at the temperature 10 to the power 15 or 10 to the power 16 GeV, took place in the universe, then magnetic monopoles would be abundantly produced, and these abundantly produced monopoles would basically overclose the universe. And in fact, it was one of the first motivations for inflation. Not to mention that one of the first model of inflation by Alan Guth was by itself a realization of supercooled phase transition. So another reason from a more modern perspective, you've heard about the discovery of gravitational waves by LIGO-Virgo collaboration, and there are also ongoing searches for gravitational wave background. So gravitational wave background is not only can be produced not only by inflation, but also during phase transitions through, for example, domain walls and cosmic strings, or they can occur during the bubble collisions if the phase transition is of the first order. And the resulting gravitational waves are very interesting because they can fall in the observable range of LISA experiment, which is currently approved Einstein telescope, and pulsar timing arrays. Some of them are currently ongoing. In that case, the frequency of gravitation, these experiments cover the frequency range from very small, like 10 to the power -8, to 100 Hertz. So then what is closer to my talk, particle emission during phase transitions can be quite intensive, and these particles can contribute to dark matter, as I will explain better in my talk. Okay, so let me start with some classical example of phase transition, which can also take place in cosmology. In phase transition, in this picture, with some scalar field. Okay, I took some real scalar field. It can be something more complicated, some scalar multiplet. The theory, which is spontaneously broken, can be complicated. Okay, generically, phase transitions are associated with symmetry breaking of the system. So here you can see there is the scalar field and its effective potential. If you will drop these temperature corrections, then the scalar field is in this spontaneously broken phase. It's a spontaneous, the potential spontaneously breaks here, Z2 symmetry. But generally, the field phi can interact with hot primordial plasma with different particles, and in that case, it requires some temperature corrections. And commonly in cosmology, this temperature correction at high temperatures, it can beat the expectation value of the low temperature expectation value of the field phi, and the symmetry at high energies, at high temperatures is restored. Then, so the field, so as the symmetry is restored, the field phi at high temperatures is sitting at origin at 0, as it can be seen here. So this is the effective potential at high temperatures, and the expectation value of a field phi is 0. But as the temperature decreases, and this is the situation in the universe is cooling down as the time passes by. And as a result of cooling down of the universe, the symmetry gets spontaneously broken. So the field phi eventually gets an expectation value, non-zero. So there are two types of situations. One is the first order phase transition. In that case, the field phi, so the field phi is sitting in the minimum, but at some temperature, the second minimum appears, which is getting deeper and deeper, and the initial minimum and this new minimum is one size of true vacuum. They are separated by the potential barrier. And in that case, in this case of the first order phase transition, the phase transition occurs through bubble nucleation. It's like in the first figure which I showed with boiling water. There can be a different case, different situation when as the temperature decreases of the universe, then the minimum where the field phi is initially sitting, it turns into the maximum. So in that case, the transition to the minimum occurs without potential barrier. So this is the case of the second order phase transition. In fact, in my talk, the separation between first and second order phase transition will be not so crucial. But what will be crucial is that is the observation that typically in cosmology, you start with zero expectation value of a field phi at high temperatures from the unbroken phase. And as the temperature decreases, the field phi, the scalar field, quickly reaches a constant expectation value in the broken phase. And then it remains in the broken phase with a constant expectation value till present. Okay, so yeah, so this is the common law in cosmology. The system evolves towards spontaneously broken phase described by a constant non-zero expectation value of some scalar as the universe cools down. So, and the canonical example is electroweak phase transition in the early universe, which is due to the constant expectation value of the Higgs field. Okay, I told you in the beginning that there is no electroweak phase transition, that's true, but just to simplify the picture. This would be the case if the Higgs mass would be a bit smaller than 125 GeV. But this is not important for my talk. What is important is that I will consider a very different situation when the scale of spontaneous symmetry breaking is time dependent over large cosmological timescales. You can imagine what the expectation value. So this is a situation is much less widely considered in the literature, despite the fact that it's known in cosmology for about 50 years. So I think it was at least in cosmology, it was Weinberg who first considered this opportunity in '74. But since then, this opportunity received some attention, but much less compared to the conventional phase transitions. And not so many of cosmological applications of this time-dependent expectation value have been studied. So, okay. But
so I guess the original idea is goes to Kirchnitz and Linde, right? Kirchnitz, Linde, but they always, since Kirchnitz was motivated by condensed matter, so they always assumed it's constant. Of course, I don't think they considered time, right?
Yes, I think generally, yeah, the basis for cosmological phase transitions, yeah, it was made by Kirchnitz and Linde, maybe also by Kirchnitz independently. And actually, in this paper, Weinberg actually is building on the construction or on the phase transitions by Kirchnitz and Linde, right? So, but
Sabir, can I ask also, the second possibility is similar to the second order phase transition on the previous transparency, right? Oh, no?
yes, you're right. Yeah. Yes, it's much more similar. But once again, I will talk a bit more about it later. But here you fall into the constant expectation value. And in this picture, I'm talking about the expectation value tends to 0. But in this sense, yeah, generally, yeah, this is described in terms of a second order phase transition. Yes, but it will be clear. It will be clear, become clear very soon.
Sorry, what's the scale of spontaneous symmetry breaking? Is the same as the value, the vacuum value of scalar, or something else?
It's the expectation value of a scalar, yes.
Yeah.
But it's just not constant. Yes, but yeah, it's you can, yeah, it will be eventually be, I will relate to it to the expectation value of some scalar field.
Mm-hmm.
This option is seemingly unnatural, seemingly exotic, but in fact it's quite natural in cosmology, because cosmology is expanding and all the physical quantities in the universe, like temperature, is decreasing with time. So if one manages the way to relate the expectation value of some scalar field to the temperature, then this kind of spontaneous symmetry breaking pattern will be realized. Okay, you can play with my colleagues. We played a bit more exotic games, like connecting the expectation value to the Hubble rate of the universe, or even completely exotic to primordial magnetic fields. But I will not consider these options in my talk. But just to show that this kind of scenario can be realized in a broader range of models. So I will give an example of concrete model with the two symmetry, which realizes this temperature-dependent expectation value. It's pretty simple. So here is the scalar field chi, who is going to be the main guy in the game. And okay, it has a canonical kinetic term. Everything is simple. It has the bare mass term with constant m squared. It has generically the quartic self-interaction. And here is a bit less trivial guy. It's what is in the dark matter community is called sometimes portal interaction. It's the field chi square. The field chi is interacting with some field phi. I will not make many assumptions about this field phi, but I will assume that it is in thermal equilibrium with hot plasma. For simplicity, you can think that it is a Higgs field, but it will a bit restrict the phenomenological applications of what I'm going to talk about. But at the same time, while the field phi is hot, it's in thermal equilibrium with plasma, the field chi is cold. So this is achieved by this coupling constant G squared, the portal coupling constant. I will always assume that it's very weak, very small. Then about self-interaction. So here is one more important point, that the portal constant G squared is, I will choose it positive. And you can see what's, due to this choice of sign of G squared, if I will take a look at this interaction, it kind of introduces instability in the model. My potential becomes unstable. But this instability is tamed if by the quartic self-interaction and the possible quartic self-interaction of a field phi. So to tame this instability triggered by the constant G squared, I should assume that the self-interaction is not very small. So it's larger than G to the power 4 over the quartic self-interaction of the thermal field phi. It's in fact, it's just Sylvester criterion for the positivity of the applied to the our potential. Okay. So, as I said, the field phi is thermal. Therefore, at very high temperatures, if I will also assume that it's sufficiently light at high temperatures, it has a non-zero dispersion due to thermal fluctuations. Here, n is the number of degrees of freedom associated with the scalar multiplet phi. For example, if you will take the case of a Higgs field, then n will be equal to 4. And these thermal fluctuations of the field phi, they introduce the thermal correction to the effective potential of a field chi. So here is crucial that here becomes crucial why I have chosen the Portal constant g squared to be positive, because in that case, this thermal contribution to the potential of a field chi, effective potential, will go with a negative sign. As a result, at very high temperatures, now take very high temperatures, this thermal correction will beat this mass term where m is constant while temperature is increasing as one goes back in time in the universe. This means that at very high temperatures, the ZT symmetry will be broken. And the field chi will acquire this expectation value. Okay? And this expectation value is apparently it's changing with time because it relies on the temperature, which is decreasing with the scale factor of the universe. So there are two possible scenarios. One is that symmetry restoration and another symmetry non-restoration. So let's again take a look at this expectation value, and symmetry restoration will take place if m squared, the bare mass squared of the field chi, is positive. M squared is positive. In that case, eventually the temperature will decrease. Eventually it will hit this mass term contribution, and the expectation value will go to 0. At this point, inverse phase transition will take place. Okay. Another possible scenario, which seems to be less interesting, is that happens in the case is if m squared is less than 0. In that case, symmetry remains broken at late times, and the expectation value tends to a constant value. This actually is also a very interesting scenario, and probably I will consider it closer to the end of my talk. And in the main part of my talk, I will deal with this scenario with the inverse phase transition, when the symmetry is restored at sufficiently low temperatures. Why? Which applications could one get from that? It's actually, here I'm coming to there are many applications. And the first one, and it's my storyline one, is that inverse phase transition can lead to the dark matter production. So it's based on my paper with Evgenia, Dmitry Gorbanov, and Alex Wittman. So assume that, as I said, at high temperatures, the field chi is in the spontaneously broken phase, because large temperatures source the non-zero expectation value of the field chi. But as the temperature will decrease, the field chi, which is the expectation value, will move towards 0. Initially, this field chi is sitting at the minimum of spontaneously broken phase, and it tracks the expectation value, which is changing the scale factor of the universe. It just tracks the minimum of its expectation value. But this process cannot continue right until the moment of symmetry restoration. The reason is as follows. The reason is that if you will take the derivative of expectation value, you will see that the time derivative or the temperature derivative, it explodes as the expectation value tends to 0 and the symmetry is getting restored. So this shows that the field chi, in fact, cannot track the minimum down to the time of symmetry restoration. If it would do like that, it would get the infinite velocity, clearly unphysical result. What happens in practice is that slightly before the moment of symmetry restoration, the field chi gets offset from its minimum and starts oscillating. And these oscillations continue already in the symmetry restored phase. Okay, what can I get from this newborn oscillations? So clearly the symmetry is restored, that means two symmetry restored, plus I assumed that there are only feeble couplings involved in the model. And these two conditions clearly protect stability of oscillations of the field chi, which survive till present and give contribution to dark matter. So this is you can think about it as a new source of dark matter. These oscillations contribute to dark matter. Yeah, and Dima, as according to your question, yeah, indeed, it's the second order phase transition, because as the expectation value goes continuously to 0, its derivative with time explodes. So it's the picture which you have with in the case of second order phase transition. Okay.
Yes, thank you.
So, okay, this is just another way to phrase this result. That's the picture produced by Alex Wickman, and he's always complaining if I don't insert them his picture in the talk. So it's just a paraphrase. It's the field chi. Here it's tracking the minimum of a potential, but then it gets offset from the minimum and starts oscillating. S star is not very important. It's the ratio of mass divided by the Hubble. Don't pay attention. So in fact, the initial amplitude of oscillations can be fully determined in terms of the model parameters. And given we know how much dark matter we need. The dark matter should constitute 27% of the energy budget of the universe. And this fully fixes, the model parameter space. So this is the constraint, the mass of the field chi, low energy mass, and this is the portal constant G. And here I introduced the constant beta, which is just the ratio of quartic self-interaction over the constant G to the power 4. This constant beta can be very large, but it is bounded from below by it cannot be much smaller than unity because of the is basically again the Sylvester criterion, which protects the instability, the system from runaway. Okay, so here I kind of emphasize writing the abundant constraint like that. I kind of emphasize that I'm interested in very light masses of dark matter, and I'm very interested in very small constants, coupling constants. And this is, as I will discuss shortly, it's a kind of unusual fact that you can produce dark matter for so extremely small constants. But here I would like to say that in principle, you can deal with much larger masses. So once again, the constant beta can be much larger than unity, and you can deal with GeV dark matter, etc. This constant G can be also much larger than 10 to the power -8. But still, we have been interested in so small masses and very feeble constants. There are many reasons for that. And one of the reasons is that the same model which I introduced initially with the field chi and with this portal coupling to the thermal field phi, it actually can produce dark matter in at least two more ways. First, the most well-known and the most famous mechanism is the so-called freeze-out mechanism. Maybe if you have not heard the word freeze-out, maybe you have heard the word WIMPs, which is directly related to this freeze-out production mechanism. WIMPs are commonly it's weakly interacting massive particles, which are typically in these mass of ranges and which have a relatively large constants with the primordial plasma. These constants are so large that initially the field chi is in thermal equilibrium due to these large couplings, and due to these large couplings, there are good prospects for testing this dark matter. That's why WIMPs and freeze-out mechanism is usually the kind of thought as the frontier of dark matter physics. But so far, no dark matter has been found. It doesn't mean that there is no need to search for WIMPs anymore and no need to be interested in freeze-out mechanism. There is still ongoing research. There are still experimental facilities. However, if you check her page, General Archive, you can see that there is a larger and larger interest in different kind of scenarios with very feebly coupled particles or very light particles, or instead extremely heavy particles like primordial black holes, etc. This is not completely accidental. This is exactly because of the null result of searches for these WIMPs. So that's motivated in particular this freezing mechanism, in which case the coupling constant, the portal coupling constant is very small, so small that the field chi never reaches thermal equilibrium with plasma. Still, it can be produced by scattering of the phi particles. But what has not been known is that, to the best of my knowledge, is that when you go to the constants much below g squared, much smaller than this 10 to the power minus 11 freezing value, then you can still produce dark matter in the right abundance to explain the observations. So so the mechanism which I described before is actually operating for these extremely small coupling constants, dark matter from inverse phase transition. And this kind of enriches the parameter space where dark matter can be searched for. So this is the parameter space. You can see that there is a freeze out line. It's corresponding to relatively large values of a constant g. There is a freezing line corresponding to smaller values of g, and below the freezing line, there is still a huge parameter space where you can produce enough of dark matter, despite that it's very feebly coupled to hot primordial plasma. Okay, but the bad news is that when you decrease the coupling constants, then your chances to detect a particle apparently become smaller and smaller. And this is a problem, for example, for the freezing mechanism. That's why not everyone likes it. But here you can see that there is something slightly different. At least in the, you can see these green stripes in the corner of a parameter space, which corresponds to this GW here corresponds to gravitational waves. So there is a small piece of parameter space where you can probe extremely small coupling constants with gravitational waves. And this brings me, and I will explain the origin of these gravitational waves in the second part of my scenario, of my talk, which is directly connected apparently to the previous one, but which can be also understood separately. So this is the picture we so-called melting domain walls. So where do these domain walls follow from? It is known from the classical paper by Zildovich, Okuny, and I think Kobzarev, that in the situation when the Z2 symmetry is spontaneously broken, domain walls typically appear. And these domain walls occur if prior to falling into the spontaneously broken minimum in the very universe, I'm talking about the times well before the inverse phase transition. If you're prior to fall into the spontaneously broken minimum, the field, the scalar field is at 0. By the way, it's not so trivial to place this field to 0 in the scenario which I considered. It requires some small extension at least. And this can be achieved by non-trivial coupling of a field chi to the Ricci scalar. Then during inflation, it will relax to 0. But I don't want to overcomplicate my scenario. Just assume that in the post-inflationary universe, the field chi is sitting at 0. Then what happens? At some point, it will fall into a spontaneously broken phase, and it has two options. Either it falls to the minimum with a positive value of expectation value, or it will fall into the minimum with a negative value of expectation value. And if this happens, then the regions of the space separate the regions of space carrying different expectation values of a field chi will be separated by domain walls. So which are two-dimensional, highly energetic objects, and you may have, if you have not learned a lot about domain walls, in any case, you probably know them very well from the course of classical gauge theories under the name of king. To be more precise, kings, this non-trivial scalar field configuration, is basically a domain wall is a king embedded in 3+1 dimensions. So this is the scalar field profile inside of domain wall. And Z is the distance from the center of domain wall. If you go to plus infinity, the expectation value is just plus the average of chi. And if you go to minus infinity, then it's a negative expectation value with a negative sign. Okay. So another important characteristic of domain walls is tension. So tension is basically the wall mass per unit area of a wall, which is directly related to the expectation value of a field chi and the quartic self-interaction. There is another interesting fact about domain walls, and is that okay, so imagine that you produce domain walls in some patches of the universe, but as the universe expands, these domain walls meet each other and they can collide, merge. Some complicated process is going on, but the end point of this process is the so-called scaling regime. In the end of the day, there will be one or a few domain walls in the horizon volume. So if domain walls, for example, form today, then in the whole huge universe, there will be one, maybe a few domain walls, which was confirmed by numerical simulations I did a long time ago. And this scaling regime, once the domain walls are in the scaling regime, then the domain wall network is essentially described by just one parameter, the Hubble radius. And this allows to estimate the energy density of domain walls, which is basically the domain wall tension times the Hubble rate of the universe. And there is a big problem with that. Because as it follows, for example, if I assume that the expectation value is constant, like in the standard phase transitions, then the energy density of a wall network will scale. It's proportional to the Hubble rate, and the Hubble rate is proportional to temperature squared of the universe. I'm talking about radiation-dominated universe. And in that case, the energy density of walls related to radiation will grow with time very fast. And they will eventually overclose the universe. So the universe will be dominated by radiation instead of, by domain walls instead of radiation. Clearly, it's not what we get from observation. And this is called the, this is essentially the infamous domain wall problem. Okay? So, but in our case, there is no domain wall problem, exactly because the expectation value changes with time, decreases with time, hence the domain wall tension changes, and the energy density of the domain wall network behaves in a different way. So the domain wall tension drops with the temperature to the power 3, the cube of temperature, and then the energy density of a domain wall network will drop as temperature to the power 5. As a result, the energy density of a domain wall network, melting domain walls due to the time decreasing expectation value, will drop faster than radiation. So if domain walls give initially small contribution to the energy budget of the universe, they will remain negligible at later times. In fact, this solution for the domain wall problem arising in some models. This fact that in some models, these domain walls are harmless, it has been emphasized also a long time ago by Alex Vilenkin. Moreover, the domain walls are not only contributing negligibly to the universe, but also they completely vanish at inverse phase transition. So, but what can we get from these domain walls? And actually, Vilenkin wrote in his paper that these domain walls are quite useless. But here we kind of slightly disagree. And we say that domain walls, melting domain walls, can still leave trace in the universe. Okay? Through gravitational waves. It's actually an interesting fact that the gravitational wave emission by domain walls can be estimated like very simply using just the some how they call the scale configuration. Okay, very simply. Okay, so it can be estimated simply using the Einstein quadrupole formula. So you know Einstein quadrupole formula. This is the quadrupole mode, quadrupole moment of a network of domain walls, and this quadrupole moment can be estimated simply as the just based on dimension considerations. Okay, it should be proportional to the domain wall tension, and based on the fact that there is only one length scale in the problem, the Hubble radius, then you can obtain this expression for the quadrupole moment. Then the energy density of a gravitational waves can be also simply estimated, and it just relies on the domain wall tension squared over the Planck mass squared. So these are very rough estimates. They show actually that most of gravitational waves are emitted at the moment of domain wall formation, because once again the tension is decreasing as cube of temperature. It is, once again, it's very rough estimate, but remarkably, the more like numerical simulations which have been running quite recently by this.
Excuse me, Sabir,
Yeah.
can I ask a question?
Sure.
If you look at your formula for the average of chi, okay, for the vacuum value,
Yeah.
you see that the symmetry is stored at a given temperature. So kind of
Yes.
the domain walls should disappear at this temperature.
Yes.
Why do you say that they are kind of the chi vacuum value of chi is proportional to temperature? It should be zero if temperature is smaller than something.
Yes. Yes. Yeah, and it will go to zero. Yeah, expectation value and domain walls will disappear, and that's fact. But here is an important point, which I just said, is that most energetic gravitational waves are emitted right after domain wall formation. So you can forget about later times when domain walls will disappear. And at very early times, you can forget about the bare mass term. And chi is really just proportional to the temperature.
Okay, thanks.
Yeah, I'm talking about very early times, which are only relevant for this kind of phenomenology. So actually, the rough estimate, just based on the Einstein quadrupole formula, it matches remarkably well numerical simulations by this gentleman. Okay, we don't have an alternative numerical simulation, so we just relied on these numerical simulations. And these guys showed that within a factor 2, the energy density of gravitational waves is indeed given just by sigma squared of wall divided by Planck mass squared. And the frequency of gravitational waves at the emission is just about the Hubble rate of the universe. So, okay, we didn't have a choice but to rely on this result. And I want to say that these numerical simulations are, of course, have been performed for normal cosmic strings, for normal domain walls, sorry, with a constant tension. These guys assumed that the domain walls, I said that the domain walls with a constant tension are problematic for cosmology. But these guys assumed that somehow domain walls disappear at some point. And then we estimated the energy density of gravitational waves of this unstable domain wall network. And we literally use the result. So take this with a grain of salt, what I will show later. But anyway, we think we justified this by the fact that, like in the case of these guys, most of gravitational waves by domain walls are emitted within a short period of time. In the case of constant tension domain walls, which disappear, this is the time corresponding to the just before dissolution of the domain wall network. In our case, it's the time just after the formation of the domain wall network, but it doesn't affect the estimates of peak frequency and peak energy density of gravitational waves. So there is
sorry, very naive question. I probably missed this. So inflation is kind of happened earlier, right? So you're discussing what happens after.
Yes, yes, yes.
Okay, yeah, because there was an argument about domain walls that early universe domain walls, that they should kind of be diluted by inflation, right?
Yeah, if they have been formed before inflation, they will be diluted.
Yeah. Okay.
In our case, yeah, we want domain walls to take place because we.
Yeah.
So, okay, we took the results of numerical simulations and estimated the energy density and peak frequency of gravitational waves. And this is actually quite funny thing which is happening is that the peak frequency of gravitational waves if we take the constant, the portal constant to be of the order 10 to the power minus 8 or smaller, it falls in the frequency range of current and future observatories. Just to remind that about 100 Hertz, it corresponds roughly to the LIGO-Virgo frequency band. But it will also correspond to the frequencies of Einstein telescope. If you will go below, you will meet LISA or pulsar timing arrays. It's kind of a funny fact that weaker coupled regime we consider most more ways we have how to test our model with gravitational waves. Instead, if we would consider much larger G, we would deal with very high frequencies of gravitational waves, which are not covered by the gravitational waves observatories. So basically, weaker couple sometimes means that we are more visible in the more visible range. But of course, not only peak frequency, which is relevant, but also the energy density of gravitational waves produced, and which is generically quite small. It's quite small. It's much smaller than what you can probe with LIGO, but it can be in the range accessible by LISA of Einstein telescope. It relies on the constant beta. I recall that beta is lambda over g to the power 4. And we need to be really lucky that, in some sense, we need to be lucky that if the constant beta is close to unity, it should not necessarily be, it can be much larger. But if it's close to unity, then we can be in the observable range. So this is just to illustrate this using predictions of our model versus sensitivity curves by gravitational wave observatories. Here you can see Einstein telescope, Tianqin, which is currently, I think, approved. LISA is approved. DeSigo, I don't know if it's approved or not. There is IPTA, which is ongoing. There is a future SKA. So for some range of model parameters, quite a narrow range, you can probe the model with gravitational wave observatories. It's like, and this is remarkable that it happens in a very weakly coupled regime, and probably this is the only chance how one can probe these kind of models. Otherwise, of course, at colliders or somewhere like that, it's meaningless to say about the possibility to test these models. So, okay, actually what is shown here, in our paper, we estimated just the maximal, the energy density of gravitational waves at peak frequency. What is also interested for experiment is the shape of gravitational wave spectrum. Here I will not spend much time because we have just preliminary considerations that the shape of the spectrum of gravitational waves produced is different from the spectrum of gravitational waves produced by constant tension domain walls and probably by most other sources of gravitational waves. But this is something not based on numerical simulations. These are just our theoretical speculations, and I will not spend much time on it. So it's like the work in progress. Okay. This is finally, I would like to speak about, if your time permits, if I have 5-10 minutes more, then I would like to speak about the last storyline. So as I told in the beginning, we are so far I have been interested in the situation where the expectation value of a field phi is decreasing with time, and eventually inverse phase transition is happening. But the situation can be different, and the symmetry, the expectation value is decreasing with temperature, but eventually it stabilizes at some constant value, which seems to be a more boring scenario, but in fact it has some, in my opinion, possibly interesting applications for axions. And that way it is based on my paper from 2 years ago with local postdoc Rom Samantha. So here I will not go into any details, and probably I will target only the part of audience which is familiar with axions, but just a couple of brief facts about axions. So these are very light particles which are introduced to particle theory and to the extensions of the standard model in order to resolve strong CP problems of quantum chromodynamics by Piché and Quinn. Axions should be thought as the pseudo-number Goldstone bosons of spontaneously broken anomalous U1 symmetry, which is called exactly Piché-Quinn symmetry, after the name of the inventors. So you kind of introduce into the model the complex scalar field globally with a global charge, global Piché-Quinn charge, and here A, the phase, is basically an axion. So axions, so Piché-Quinn symmetry, one Piché-Quinn symmetry is slightly broken by QCD instanton effects, due to which the axion receives a potential, non-trivial cosine-like potential, and eventually, and it can be, this potential corresponds to the small mass of an axion. And given that an axion has a small mass, given that its stability on cosmological timescales, it's often considered as a promising dark matter candidate. Promising because it kind of resolves two problems at once. One CP problem of QCD, and another is a dark matter problem. Okay, and the Piché-Quinn field, dynamics of Piché-Quinn field is basically described, can be, I assume that it is described by the same model which I introduced in the beginning. So it's the same model with a portal interaction with some thermal field phi. The only difference is that I've been dealing with Z2 symmetry, and now there is U1 Piché-Quinn symmetry. So the story is pretty much the same. At high temperatures, the Piché-Quinn scale, which is basically the expectation value of the Piché-Quinn field, is temperature dependent, and it decreases with the universe temperature. But at low temperatures, here I will assume that the field phi is like, it's a Higgs-like field with a non-zero expectation value. And in that case, the Piché-Quinn scale will relax to the constant value fixed by a constant expectation value of the field phi. So in this picture, Piché-Quinn scale is kind of gliding in the universe from sub-Planck values to relatively small values as the universe cools down. Why this all can be relevant? So this is relevant because this may have a dramatic effect on axion dark matter production mechanisms. There are at least two well-known axion production mechanisms. One is the misalignment mechanism. Another is due to decay of global topological defects. Doesn't matter. Matters is that these mechanisms assume a relatively large low energy, low temperature value of Piché-Quinn scale. But on the other hand, much smaller values of Piché-Quinn scale can be very interesting for supernova observations or also horizontal branch star. So with these huge values, phenomenology of axions can be relatively poor. Dima can argue with me about it. He knows more. In our paper, we targeted the possibility to generate the right abundance of QCD axion dark matter with relatively small values of Piché-Quinn scale. And this is indeed possible, and this kind of early time temperature dependence of Piché-Quinn scale, it's indeed opens up a possibility for efficient axion dark matter production, new mechanism in the early universe. In fact, this axion dark matter production is very similar to the parametric resonance after inflation. So when the radial field the modulus of a Piché-Quinn scale relaxes to the minimum of this spontaneously broken phase in the early universe, set by the Pichet-Queen scale. In the post-inflationary universe, it's generically upset from the Pichet-Queen scale, but at some point it relaxes to the minimum of spontaneously broken phase. And during these oscillations, like during inflation oscillations, you produce particles. In that case, oscillations of a radial field produce axion particles. And there is actually a funny thing about this parametric resonance, which is very different from what you have typically in inflation. So compared to inflation, the resonance band is stable because the redshift of produced axions is compensated by 10 degrees of the Pichet-Queen scale. As a result of this axion production, even if it occurs in the regime close to the narrow parametric resonance, is extremely efficient and leads to the explosive production of axions within some few Hubble times. So you quickly produce particles which later on play the role of dark matter. So yeah, but there is a subtlety. So we did not run real lattice simulations. What we did is actually like the simple simulations which neglected back reaction of produced axions on the radial field. And this back reaction may have some effects which we cannot account for. In particular, it may happen that along with axions, the radial particles ρ are also produced. But doesn't matter. So what I will finalize with the parameter space for the model in terms of the expectation value of a thermal field phi and the low energy Pichet-Queen scale. And the funny thing is that the model is actually practically excluded. So the thing is that we are uncertain about, as I said, the back reaction issues and radial particles being produced. And if it turns out that the number density of radial particles produced in the narrow parametric resonance along with axions is quite huge, then our model is on the way to be rolled out. Even if it's 1% of radial particles is produced, then we are left with a very small range of parameter space, which as nevertheless we think is quite interesting for the stellar searches for axions or like experiments like TASTE or IAXO. But to understand what is the real number density of produced radial particles, it's like a few, it's a future prospect, and it will decide eventually what is the fate of this axion production mechanism. So let me conclude. The main idea of my talk was that the spontaneous symmetry breaking in the universe can have a time varying expectation value, and this scenario can have a lot of phenomenological applications. In particular, it can help to generate the right abundance of dark matter in a feebly coupled regime. It can help to get rid of domain wall problem and at the same time enjoy potentially observable gravitational waves from domain walls. With these gravitational waves, one can probe the underlying field theoretical model in a very weakly coupled regime, inaccessible by other experiments. And finally, I mentioned that with this symmetry breaking pattern, one can generate axion dark matter in astrophysically interesting range of Pichet-Queen scale values. So that's it. Thank you very much for your attention.
No, thank you. Are there any questions?
Sorry,
Can I ask a question about the tracking solution for domain walls?
Yes.
You used a tracker solution which is known to be a attractor, right?
Yes, scaling solution.
So that scaling solution. Sorry. So starting from any concentration of domain walls, with time you attract to this solution. But you have a finite time where you have domain walls. So the question is whether did you estimate whether this time is enough to approach this solution?
Yes, it's a good question. So from the moment of domain wall formation, of course, it takes some time before the scaling regime will be achieved. Yeah, but this happens. These guys they have they estimated this time because you can understand it only from lattice simulations. So they performed these lattice simulations, and as far as I remember, this scaling regime is achieved when the width of domain wall, which was constant in their case, while the horizon radius is growing, when the width of domain wall is becoming of the order 0.1, 0.2 of the horizon radius. So once this is a rough condition is achieved, then they observed that the domain walls have been in the scaling regime. So it should be a small fraction of a Hubble radius, then it happens.
But this is the only parameter because you have a specific initial condition, right?
Yes.
So that your domain walls appear during a very specific phase transition. Probably there might be, I can imagine that there are too few of them, for example. And then you will not expect fast approaching the scaling regime.
Well, initially we creating about one domain wall per horizon. To be honest, I don't know in which sense our estimates would be different compared to the result of simulations of these guys. Well, let me think.
So you are saying that you are approximately near the scaling solution from the very beginning, right?
Yes, but here is
Okay.
one thing. You see here there is a parameter b. In fact, this parameter b, which is actually not very small, but it leads to the decrease of energy density of gravitational waves. And in fact, it takes into account the finite time of a roll of a field chi to the minimum, but it also takes into account the fact that it may take some time for the scaling regime to happen. So we kind of introduce this phenomenological parameter to be honest. So, but in fact, yeah, you can say that if what you say, if it takes crazily a lot of time for the scaling to happen, then you should take this parameter b to be extremely large, and then of course you will get much smaller number of gravitational waves. So we are keeping this in mind. Yeah.
Okay, thank you.
Other questions?
Nothing is clear, but I wish I could ask something useful. No, it's
Sorry, I've been
it's very good talk. No, it's very good talk. Thank you very much. Yeah, so you were very clear. At least.
Thank you.
Can you maybe just to repeat again? So the thing that summarizes all these three discussions is this potential, right? This particular potential which allows you to generate this dependence. The potential changes in a suitable way when temperature changes.
Yes. So yeah, this is the potential I've been playing. So one scenario which I can see that it's when you are sitting here and then spontaneous symmetry breaking. Symmetry is restored. It's one. Another scenario is when you are on top here and then you fall in this spontaneously broken phase. It's domain wall. And the third scenario is when the symmetry is not restored, but this expectation value stops at some point and stabilizes at some constant. So these have been the three scenarios. Yeah, but they can be understood just from this simple picture.
Yeah, and the novel thing is this phi squared chi-squared term, right? The thing which allows you to do this.
Yes, yes, yes. So, yeah, I want to emphasize again that the expectation value temperature dependence is again not something completely new, but what was new is maybe a concrete model. But similar models have been considered in a bit different from a bit different prospects. Yeah, but people considered these patterns, but they didn't consider don't consider so much the phenomenological applications, I would say.
Mm-hmm.
I would say that the interaction is standard. This is a scalar portal.
Yes, yes.
But what is new for me is that they noticed that if you have a restoration of symmetry, then something remains, some oscillations remain.
Yeah.
So
Exactly. This oscillation. Yeah, this is new definitely for dark matter. Yeah.
But this non-minimal, you mentioned non-minimal coupling, so it's important for you to have this fine-tuning or the value.
Non-minimal coupling to gravity.
Yeah.
Yes. So the thing is that I'm dealing with a very light field, and in the inflationary universe, then the scalar field will acquire a huge expectation value, which will be correlated at large cosmological timescales. And in these situations, domain walls are not formed. So you will be sitting here, somewhere here, for example, in the post-inflationary universe, and you will fall just in one minimum, and then the domain walls will not be formed. So that's why I don't know, artificially or not, I assumed, yes, that there is a non-zero coupling, non-minimal coupling to gravity. And in that case, the field chi has a super Hubble mass during inflation, which makes it relax to zero at inflation. So this, in the post-inflationary universe, in our model, it will sit at zero. But it's like, yes, so kind of to enjoy the domain wall phenomenology, you should, one should extend the model slightly, exactly by this non-minimal coupling.
Completely unrelated to your talk, probably. Do you know about papers by Neil Turok, who is a bit crazy, about some CP invariant universe or something like that? It's alternative to inflation. Have you seen that?
To be honest, I didn't track his last paper. So
okay.
From 20 years ago, I know I'm familiar with his papers.
Yeah.
But,
no,
a decade ago, I stopped to track them.
Yes, it was like, well, he wrote various crazy papers, but that was more recent. Yeah. Anyway, yeah.
Yes. It was related to baryon asymmetry. Or...
Yes.
Okay.
Okay, last call for questions. Okay, thanks. There are no more questions, so let's thank the speaker again.
Yes, thank you very much. Thanks a lot.
Yeah, and goodbye.
Okay, bye.